Section 5.5 is on normal approximations to binomial distributions. Now I have to review with you, remember when we did binomials a while ago. For instance, like say you had a problem or 10 problems on an assignment and it was either right or it was wrong. So binomials, remember, are two possibilities, your NPQX. So say you have 10 problems on an assignment. Your probability of getting it right, let's just say like it's an A-B choice, just to make it easy. So you have a 50% chance of getting it right and a 50% chance of getting it wrong. What's your probability of getting 6 problems correct? Okay? So you went to binomial PDF on your calculator. Remember, binomial PDF is NPX. So it would be 10, 0.5, 6. Okay? But what this lesson does, what if we have 100 problems? 50-50 shot again. Let's say we want to figure out what's the probability of getting between 6 and 85 questions correct. That would be a lot of work if we did binomial PDF. We'd have to do it 10.5, 6, 7, 8, 9, 10, 11, and so on, all the way up to 85, and then add all of those up together. So that would be pretty annoying. So that's what this lesson is on, normal approximations to binomial distributions. So we're going to take a binomial and we're going to make it a normal approximation, a normal curve. And we want to find what's the probability between 6 and 85 of these being right. Find that whole area in there. Okay? So that's what the whole lesson is on. Determining whether the normal distribution can be approximated. So there's kind of a rule first here. Can we even use this? Find the correction for continuity. I'm going to give you a little heads up since this is a video. There's going to be this plus or minus 0.5 that we have to do. Okay, kind of tricky. Use the normal distribution to approximate the normal probabilities. The normal distribution is used to approximate the binomial distribution when it is impractical to use binomial distributions to find a probability. So between 6 and 85 questions right, that's a lot of work. So when it's impractical to use the other ones. It's not that it won't work, binomial PDF will work. But it's just a lot of work to do it. Okay, a couple of rules first. To even be able to use this, your n times p and your n times q have to be greater than or equal to 5. If that's not true, then you can't use the normal distribution. You have to use the binomial PDF. So that has to be true first. Your mean is still, it's been a little while, but your mean is still n times p, and your standard deviation is still the square root of npq. By the way, you can absolutely take notes with me right now. All right, so here's just kind of what happens. This whole rule about n times p and n times q have to be greater than or equal to 5. If your n is small, your n times p is small, your n times q is small, so these are not greater than or equal to 5. Look what happens to it's not symmetrical. It's not a bell-shaped curve at all. As it gets bigger, as the n gets bigger, from 4 to 10, it's starting to approach it. Still a little too small though, still not 5. And here we go. They're finally starting to look bell curved. So this n times p, n times q is greater than or equal to 5. So as n increases, the histogram approaches a normal curve. Decide whether you can use a normal distribution to approximate x, the number of people who replied yes. If you can, find the mean and standard deviation. Not that you can't find the mean and standard deviation. You still can find the mean and standard deviation if n times p and n times q aren't greater than or equal to 5. Okay, so 51% of adults in the United States whose New Year's resolution was to exercise more achieved their resolution. The random selection of 65 adults in the U.S. whose resolution was to exercise more, and ask each if he or she achieved that resolution. So find your NPQX again. N is 65, 51%, and 49, your P and your Q. So if you take N times P, 65 times 0.51, you get 33.15. So greater than or equal to 5, so far so good. Then takes N times Q, and you get 31.85. So yes, it is normal. Okay, as long as N times P and N times Q are greater than or equal to 5, you can make it a normal distribution. So let's find the mean and standard deviation. The mean is that N times P. So the mean is 33.15. Standard deviation is the square root of 65 times 0.15 times 0.49, which is approximately 4.03. Oops, remember that one. One more. 15% of adults in the United States do not make New Year's resolutions. You randomly select 15 adults in the US and ask if he or she made a New Year's resolution. Right away I see kind of some smaller numbers. 15%, 15, so I've got maybe something I need to watch out for here. So N times P, which is 15 times 0.15, is sure enough only 2.25. So you don't even have to find N times Q because this one right away says not normal. You could still use binomial PDF, but you cannot use a normal curve. Okay, this correction for continuity, and I gave you a little heads up, this is that point, give or take 0.5 thing. The binomial distribution is discrete and can be represented by probability histogram. To calculate exact binomial probabilities, the binomial formula is used for each value of the x and the results are added. So that's that binomial PDF that I've been talking about. Binomial PDF NPX. I believe there are 1 or 2 in your assignment that you have to use binomial PDF because N times Q and N times P are not greater than or equal to 5. Geometrically, this corresponds to adding the areas of the bars inside the probability histogram. So it kind of rounds off this space in here, kind of give or takes from that space. So it kind of rounds off to be this bell curve. When you use continuous binomial or normal distribution to approximate a binomial probability, you need to move 0.5 units to the left and right of the midpoint to include all possible x values in the interval. This is your correction for continuity. So that example I used at the beginning when I talked about if you wanted to get 6 problems correct. Well, this 6, only way to do this on a bell curve is to give or take 0.5 each way. Now, I mean, I don't know who came up with this rule, why they didn't give or take 0.1. It's just kind of the rule of it. So to find that area in between, which is just the 6, you would give or take 0.5. So 0.5 each direction would be 5.5 to 6.5. So to be able to include that one value, because we're going to have to do this normal CDF, what's your lower z to your upper z? Well, you have to give or take, you don't have just one value when it comes to normal CDF. You have to find that area in between by give or take that 0.5 each direction. So, okay, let's just practice with that. I'm not going to get into probabilities or the z-scores or anything quite yet. Use a correction for continuity to convert the binomial intervals to a normal distribution interval. The probability of getting between 270 and 310 successes inclusive, kind of a key word there. So that includes 270 and includes 310. So if you looked at this on a curve, and I don't know what the mean is, I'm not getting into that yet, but it would be like, okay, 270 to 310. If I want to include that and include that, I have to back up 0.5 this direction, and I've got to go forward 0.5 this direction to be able to include that 270 and to include the 310. So we're going from 269.5 to 310.5. So that would include that 270 in there and include that 310 in there and find that total area inside there. You know, you can also illustrate it on a number line. Just think of that as 270 to 310. So we have to go above 0.5 and below 0.5 to be able to include both of those. I don't know if you realize this, but everything we've done up until now has been less thans or greater thans, not less than or equal to's or greater than or equal to's. So to be able to include that, you have to be greater than 269.5 and less than 310.5. So it would look kind of like this. All the values in between there, all the discrete whole numbers within that area. The probability of getting at least 158 successes, I'll show it to you on a number line again. So 158, so at least 158 means 158 or more. So I'm going to have to back up here to 157.5. Again, notice I'm doing a greater than, not an or equal to. We don't have any formulas for or equal to, so we have to back up this 0.5 to be able to include that 158. This one's kind of tricky. The probability of getting less than 63 successes. So let's say here's 63. And remember, these are all discrete whole numbers. So the first whole number less than 63 is actually 62. So if you give or take 0.5, you're talking about right in the middle there. You're talking about 62.5 and less to be able to include that first whole number, which is 62. That's a tricky one. So x is less than 62.5. Okay, it's kind of the wording on this one. If it was less than or equal to, then we would say 63.5. But the first whole number less than 63 is 62, so we give or take that 0.5 from there. Okay, we're going to get into these steps, and these steps are going to be really important the further we go in this class. So really get these written down good. Verify that it's a binomial, which a lot of times the dead giveaway is you have an NPQ. Determine if you can use the normal distribution, which we talked about a little bit ago. N times P and N times Q both have to be greater than or equal to 5. If you can't, if not, then you use the binomial PDF. Find the mean and standard deviation. Sometimes they give it to you in the problem, sometimes they don't. You got to find it. Apply the appropriate correction for continuity. So do your plus or minus 0.5 each direction. Find the corresponding z-scores. Just use your z-score formula. X minus mu over sigma. That's why we need X minus mu over sigma. That's why we need mean and standard deviation, is to be able to plug it into that formula. And then find the probability from there, which that's when you do that norm CDF. Your lower z to your upper z. Or you can use your